Hello, everyone, and welcome to the lecture on the E2 reaction. Now, depending on the edition of the book that you have, this might be chapter 8, or it might be contained also in chapter 7, along with SN2 and SN1 and E1 reactions. So I'm using slides from the 3rd edition of the book, which is why it's called chapter 7 on my slides. But again, if you have edition 2, then this would be included in chapter 8. So just make sure to find the section on E2 reactions, and that's what we'll be talking about starting today and also continuing into the next class period. Okay, so recall that we can treat alkyl halides with a strong nucleophile and it will do an SN2 reaction. So now we're going to be talking about what's called an E2 reaction. And an E2 reaction utilizes an alkyl halide or other good leaving group, in addition to use of a strong base. So when a strong base is used, what can happen is what's called a beta elimination or a 1,2 elimination, and it forms an alkene product. So the strong base can take a proton or do a proton transfer on the beta carbon. The beta carbon is a carbon attached to the alpha carbon, and the alpha carbon is the carbon attached to the leaving group. So the strong base can do a proton transfer from the hydrogen attached to the beta carbon. The electrons from that carbon-hydrogen bond will flow down to form a double bond between the two carbons and will have simultaneous loss of a leaving group. So just like an SN2 reaction, E2 reactions occur all in one step. And hopefully you'll recall that that's called a concerted mechanism. So again, a concerted mechanism is a mechanism that happens all in one step. You can see the mechanism drawn out here. So again, the strong base does a proton transfer. Electrons flow to form a pi bond and loss of a leaving group occurs. So we just call this a proton transfer and loss of a leaving group. The formation of the pi bond actually doesn't have a name for that particular part of the mechanism. Notice again that the product is an alkene. We'll get the conjugate acid of the base used, and the leaving group will typically remain as a salt, and the counter ion for that will be whatever was counter ion for the base. It's a strong base. So E2 eliminations, like we talked about, it's a concerted mechanism, which means everything is happening in one step. And since the alkyl halide and the strong base are involved in that one step, which by definition must be the rate determining step, then the kinetics are a bimolecular reaction. So that's where the 2 comes from, the fact that there's 2 molecules involved in the rate determining step. It is a second order kinetics, and the E stands for elimination. So if I asked you, in what ways is an E2 elimination similar to an SN2 substitution, and what are the differences? Maybe take a moment to pause the video and think about what you know about SN2 reactions, what you just learned about E2 reactions, what are the similarities and what are the differences? So perhaps you came up with the fact that they're both bimolecular reactions. That's definitely a similarity. The alkyl halide being involved in the rate determining step is another similarity. The difference is that the reagent is functioning as a strong nucleophile in an SN2 reaction and as a strong base in an E2 reaction. Of course, a substitution reaction is different from an elimination reaction. The products of a substitution reaction are different than an elimination alkene product. So that would be another difference as well. So let's consider a reagent such as sodium hydroxide. Sodium hydroxide can actually function as both a strong nucleophile and a strong base, which means it has the potential to do both SN2 reactions and E2 reactions. When it's functioning as a strong nucleophile and involved in an SN2 reaction, it has to access the backside of a carbon in comparison to where the leaving group is located in order to do that backside attack reaction. When it's functioning as a base, it does not have to access the backside of the alpha carbon. Instead, it just needs to access a proton on the beta carbon. So it doesn't really even need to get into the alpha carbon at all. So there's some difference in terms of when steric hindrance will play an effect. So for example, on a tertiary substrate, we know that SN2 reactions do not work well on those substrates because of steric hindrance. However, tertiary substrates are actually work well for E2 reactions because we don't have to worry about steric hindrance at the alpha carbon because the reagent will only need to function as a base and do a proton transfer at the beta carbon. So when there's steric hindrance, like for example, at a tertiary alpha carbon, E2 will be the major product and SN2 will not happen on that type of substrate. We're going to talk more about the E2 reaction, but the next section in the book actually is nomenclature. We're going to take this opportunity to cover how we would name alkenes. And the reason why it's being introduced in this chapter is because this is the first time we are looking at alkenes because they are the product of elimination reactions. So the nomenclature rules for the naming of alkenes is similar to the naming of alkanes. We still want to find the longest carbon chain, but now it must include the carbon-carbon double bond. We still want to identify and name any substituents. And we want to give a locant or a number to each substituent on the parent chain. The key thing here is that the alkene, it gets the highest priority, meaning it has a higher priority than alkyl substituents or even halogen substituents. So we need to get the lowest number possible specifically for the carbons participating in the double bond. And that's in preference to the lowest number possible for alkyl substituents like methyl or ethyl groups, or even halo substituents like fluoro, chloro, etc. And then we still want to list the numbered substituents before the parent name in alphabetical order. Remember that prefixes such as iso, this is actually a mistake. Definitely the iso should count alphabetically. The only prefixes that don't count are actually the counting prefixes. So sec, tert, tetra, any of those counting prefixes, those don't count alphabetically, but like cyclo, the C for cyclo or I for iso do count. So I'll have to fix this slide. And then we want to use the -ene suffix for an alkene. That's really important. So we're not going to name it as an alkane with the -ane suffix anymore. Instead, we're going to use the -ene suffix. And the number for the first carbon involved in the double bond should either be placed before the -ene suffix or before the parent name. So for example, before hexane, if that was the parent name. And again, these rules will make more sense as you go through some examples. Let's look at some examples. So recall that the first thing that we need to do is identify the parent chain. And it has to include the carbons that participate in the double bond, even if that's not technically the longest carbon chain. For example, the longest carbon chain in this structure is an octane. It has 8 carbons. But the parent for this would be a heptene because we must include the carbons from the double bond since that functionality has priority over any alkyl group. And again, we need to name it with the suffix -ene when there is an alkene. So then this becomes a heptene. The next is to identify and name the substituents, and you'll do that the same way that we did before. Third step is to assign a locant and prefix, if necessary, to each substituent. So for example, once you have figured out the longest carbon chain that includes the double bonded carbons, you'll look for other substituents like these 3 methyl groups, and then you will name that a 5,5,6 trimethyl, tri being the substituent. And it's important also that we give the lowest number to the sp2 hybridized carbons. That's the correct way to assign locants, as opposed to starting from the right and counting to the left, which would have given a number 2 position to this alkyl group. But recall, we need the lowest numbers possible for groups that have priority, and alkenes have priority over other alkyl or halogen substituents. And then we need to assemble the entire name. Recall that substituents go first alphabetically, and then we need to list the parent next. We do need to include the locant for the alkene. We only need the first number, because by definition, if the double bond is starting at carbon number 2, it also must be completing at carbon number 3. So we don't need to include the 3. And that 2 can either go before the hept or after the hept, but before the suffix -ene. The last thing that you want to think about is stereochemistry. With alkenes, remember that we have what are called cis and trans, or E and Z stereochemistry. And so that's an important thing to include in the name as well, because a Z alkene is not the same thing as an E alkene. Recall that there is not free rotation about the carbon-carbon double bond, and therefore cis and trans, or E and Z, are different compounds. So that difference needs to be included in the name, which is why you see this E in parentheses before the rest of the name. Let's recall how to assign E or Z to alkene stereoisomers. So we want to prioritize the groups attached to the 2 sp2 hybridized carbons in the carbon-carbon double bond. And we prioritize them based on atomic number, just like we would prioritize groups attached to a chiral carbon for the R and S designation. So here we would have carbon versus fluorine, and fluorine has a higher atomic number, so it gets priority. Between hydrogen and nitrogen, nitrogen has the higher atomic number, so it also gets priority. And when you have 2 groups that are on the same side of the double bond, we call that Z. And if they were on opposite sides of the double bond, we would call that E. Notice same side Z, which stands for zusammen, which means together in German. And N and F are on opposite sides, so we call this E, which stands for entgegen, which is opposite in German. Okay, so let's talk a little bit about alkene stability. So alkenes that are in a cis configuration have more steric strain. You can see here with the space filling model of this structure that these groups get really close to one another. The hydrogens that are pointed in the tetrahedron get really close to one another. And so that there is some steric strain associated with that stereochemistry. Whereas the trans configuration gets those groups further apart. And so it's just a little bit more stable or lower energy than the cis configuration. How do we actually quantify, though, the difference in stability? We talked about the fact that there's steric hindrance in the cis configuration that makes it higher in energy or less stable. But how can that actually be measured to confirm that belief? And the reason, and the way that we can do it is, of course, we can do heats of combustion, and then later on, we'll actually tell you there's a reaction we can do called hydrogenation that could also be used. But for now, it can be confirmed with heats of combustion. Recall that combustion is the conversion of a hydrocarbon with oxygen into carbon dioxide and water. So the products are the same for these two stereoisomers. And because the energy of the products are the same, we can compare the amount of heat given off and relate that to energy given off during the combustion process. And that works well because combustion is an exothermic reaction. So heat is being given off, and we can measure that in terms of temperature change. So what we'll see here is a little bit more energy, about 4 kilojoules per mole, is given off during the combustion of the cis isomer compared to the trans isomer. And so if you think about that in terms of an energy diagram, we can say that because 4 kilojoules per mole more energy was given off during the combustion of the cis isomer, that started out at a higher relative potential energy. And so we say that's higher energy or less stable than the trans isomer. There's another thing to consider when we're talking about alkene stability, and that is what effect does additional substitution on the sp2 hybridized carbons have on the stability of the alkene overall. And what we find, and again, you can measure this through, for example, heat of combustion studies, since these are all constitutional isomers, is what we find is that increased substitution increases stability. So you can see this increased stability line as we go from a mono-substituted alkene. And to figure out the substitution, we just look at these two sp2 hybridized carbons and ask yourselves how many non-hydrogen groups, typically carbon or alkyl groups, are attached to these two carbons. So you can have as many as 0 if all 4 groups were hydrogen, or 1, which we would call mono-substituted. Here's an example of disubstituted, but this doesn't have to be in the trans configuration. The disubstituted alkene could be in a cis configuration, or these two groups could be attached to the same carbon. So as long as between these two carbons there are only 2 non-hydrogen based groups, we say it's disubstituted. But again, there's multiple possibilities there. This would be an example of a trisubstituted and a tetrasubstituted alkene. And what we're seeing again is more alkyl groups. It leads to more alkene stability. So remember, lower energy or more stable. And the reason for this is due to hyperconjugation. So recall, hyperconjugation is something that we talked about when we were talking about the stability of carbocations. Recall that if you have a carbon with a positive charge called a carbocation, the more alkyl groups attached to that carbon, the more stable the carbocation was because of hyperconjugation, which are carbon-hydrogen bonds that are overlapping with the p orbital, donating electron density in or delocalizing electron density. So these alkyl groups, the carbon-hydrogen bonds, can also align with these two p orbitals, leading to a type of delocalization different than resonance because this is not in a p orbital, but still leading to electron delocalization and increased stability. All right, so let's talk about something called the regioselectivity of the E2 reaction. So what I want you to do to figure out if a reaction has regioselectivity is the first thing I want you to do is label the alpha carbon. So we'll label the carbon attached to the leaving group the alpha carbon, and then identify how many carbons are attached to the alpha carbon. In this case, there are 3. If all 3 of these groups were methyl, then there would be no regioselectivity because removal of any one of those 9 hydrogens on those 3 methyl groups would lead to the same alkene product. However, when there's beta groups that are different, for example, there's two methyl groups, and that's different than this ethyl group. Now we're going to have to think about something called regioselectivity, because the strong base might remove a proton on the beta carbon of the ethyl group, and it might remove a proton on one of the beta carbons that are the two methyl groups. And if it removes a proton on one of the two methyl groups, we would get this product. And if it removes a proton on the beta carbon of the ethyl group, we would get a different product. Now, note that these two products are related as constitutional isomers. So regioselectivity is when there's a reaction where more than one constitutional isomer product can be obtained, and one of those constitutional isomers is obtained in more than 50%, and the others are less than 50%. So as long as there's a major product and minor products, potentially one or more, then it's a regioselective reaction as long as those products are related as constitutional isomers. So again, this is only going to be an issue when there's different types of beta carbons, because our strong base may or may not take protons from any of the beta carbons, leading to different products. Now, what you see is that this particular reaction gives 71% of this alkene and 29% of a separate alkene. And these are labeled as what are called the Zaitsev product and the Hofmann product. Now, the Zaitsev product is the more substituted and thus more stable alkene. The Hofmann product is the less substituted and less stable alkene. Notice that this is tri-substituted and this is di-substituted. And remember that increased substitution leads to increased stability of the alkene. So what we're going to learn about is how do we know when a particular base is used, which one of the two possible products, either the more stable alkene or the less stable alkene, will be the major product. And it turns out that you can actually control the regioselectivity of E2 reactions by the appropriate choice of the base. So for example, if you chose this base, you're going to get majority Zaitsev alkene. But if you used a more bulky base, what we'll find is that we can influence it so that we get the majority product being the Hofmann product. Okay, so this is just a summary slide, right? When constitutional isomers are formed as products of a reaction, one of them being the major product, the reaction is said to be regioselective. The regioselectivity of this E2 reaction can be carefully controlled by choice of which strong base is used in the reaction. Let's look at some different strong bases here. We have ethoxide, tert butoxide, and then this even bulkier type of tert butoxide, except for now there's ethyl groups here, right? So it's not a butoxide anymore. I guess it would be a heptoxide. There's not a common name for this one though. But you can see that the difference between the bases is really the size of the alkyl group. And ethyl group by far is the least bulky. And as we go down in this chart, we get increased bulk of the R group on the base. And with the smaller bases, those tend to form the Zaitsev product as the major product. But as we move to the bulky bases, we can influence the reaction and get more and more Hofmann product. So a sterically hindered base then is said to favor the Hofmann product. And some sterically hindered bases that can be used are, the most common is potassium tert butoxide, but there are also some amine-based sterically hindered bases as well, although they're not as commonly used because they're not as strong of a base as potassium tert butoxide. These are also called non-nucleophilic bases, because recall that nucleophiles need to be fairly small to access the backside of the alpha carbon, and all of these are bulky. So these tend to react as bases and not nucleophiles. All right, let's practice the skill. So let's see if we can predict the major and minor products for the following E2 reactions. And again, what we're looking for is predicting the regioselectivity based on the size of the base used. Recall that non-bulky bases like sodium hydroxide and sodium ethoxide will form the Zaitsev product as the major product, and bulky bases will form the Hofmann product as the major product. And how are you going to know the difference between the Zaitsev product and the Hofmann product? Recall that the Zaitsev product is the more stable alkene, which is the more substituted alkene. So when you're starting to draw the products of an E2 reaction, I recommend you follow these steps. The first step will be to identify the alpha carbon and then identify the beta carbons. Only beta carbons with hydrogens attached to them will be involved in an E2 reaction because, of course, we need to remove a hydrogen attached to the beta carbon. So if there's a beta carbon that does not have a hydrogen attached, we don't need to consider it as an important beta carbon for the E2 reaction. So once you've identified the beta carbons that have hydrogens attached to them, ask yourself, if I lose a proton at this carbon, what alkene will form? Draw the different possibilities. The one that's the most substituted alkene will be the Zaitsev product, and the less substituted alkene will be the Hofmann product. Now, small bases tend to form the thermodynamic product, which is the Zaitsev product, and bulky bases are governed more by their kinetics because the steric bulk will increase the energy of the transition state and therefore slow it down if it's going for a more sterically hindered hydrogen. So as a result, the bulky bases will form the Hofmann product, which is the less substituted alkene, as the major product. All right, go ahead and pause and then see if you can work on these problems. All right, I'm going to assume that you guys have worked on these. Let's go ahead and work through them together. So we talked about identifying the alpha carbon, and we can sort of do that all at the same time if we want for these. And then identify those beta carbons. Those are the ones that are attached to the alpha carbon. For this one, I'm only going to put a beta by these two. This one is also a beta carbon, but there are no hydrogens attached to it, so it doesn't matter. All three of these beta carbons have hydrogens, but you can think of these as equivalent, because if I remove a proton here versus here, I'll still get the same product. This is the same structure, so we'll just draw in the same beta carbons. And then we're going to draw in the products if we remove a hydrogen at the different beta carbons. So we can potentially remove a hydrogen here. And if we do that, we'll end up with a double bond between those two. And we can also have removed a proton, at the beta carbon up here, and we would have ended up with a double bond there. So those are the two possible products, right? But this is what we call a small, right, or non-bulky strong base. And so if you're using a small or non-bulky strong base, the major product will be the Zaitsev product, right? Which means that the minor product is the Hofmann product. And how do I know this is Zaitsev and this one is Hofmann? The reason that I know that is because of the substitution. So this is a 1, 2, 3, a tri-substituted alkene. This is only a di-substituted alkene. Right, so make a little note of that. Tri-substituted alkene. Versus a di-substituted alkene. So again, we have to identify the sp2 hybridized carbons, right? And then think about how many carbons are attached there. So we have 1, 2, 3 versus 1, 2. That's where I got the tri-substituted and the di-substituted from. Okay, let's look at the next example. Has the same exact substrate, but this is a small non-bulky base and this is a bulky base. Right, so we'll call this small base and a bulky base. So this one is going to form the Zaitsev product as the major product. This one will form the Hoffman product as the major product. So we can just go ahead and draw those. Recall that the Zaitsev product will be formed on the larger alkyl group because it'll form the more substituted alkene, which would look like this. Right? And the Hoffman product will be formed from removal of the proton at one of the smaller alkyl groups, and it'll give a less substituted alkene. Right, so the difference now is going to be the fact that this one is major. Right, and they give different major products. So Zaitsev, Hoffman. So we want to remember small bases will give them more stable, more substituted alkene. And because there isn't significant difference in the transition state energy when this is small. But when this is bulky, the bulky base has a hard time getting into this more sterically hindered position than these less sterically hindered positions. And there's a larger difference in the transition state energy, and therefore it's more of a kinetically controlled formation of the less stable product, but it's formed faster. All right, now let's talk about something called stereoselectivity. So regioselectivity was when there was a major and minor product that were related as constitutional isomers. Stereoselectivity is when there's a major and minor product where the product are related as stereoisomers. For example, this strong base may take a proton at one of the two beta carbons and which generates an alkene, which may be you could think of this as a trans or an E alkene, or you could also form the cis/Z alkene. In this case, the more stable alkene will be the product. And the reason that it'll always be the product when there's the formation of these stereoisomers is because it is both kinetically and thermodynamically favorable with a small base to form the more stable trans isomer. Okay, now let's talk about E2 reactions that are stereospecific. So these are not stereoselective. Selective means that there is a major product and there are minor products, and they're related as stereoisomers. A stereospecific reaction only has one product. So one specific stereoisomer is formed and the other ones are not formed. So that's why it's called specific. How will you know whether or not you are dealing with a substrate that is going to have a stereospecific outcome in terms of the formation of the product being either E or Z, but not both. The telltale sign of how you will know is when both the alpha carbon and the beta carbon that will be losing a proton are both chiral centers. Notice that this substrate also has another beta carbon, but all three of these groups are methyl, meaning there's no hydrogen to possibly remove, so this beta carbon is not going to be able to participate in an E2 reaction. So the only beta carbon with a hydrogen is this one, and since there's only one, and this is a stereocenter, and this is also a stereocenter, then the reaction will be stereospecific. And it turns out that in this particular case, it is not possible to form both stereoisomers, which could be called E and Z, but only the E isomer is formed. So there's only one product that happens to be the E isomer. Recall that it's E because of the priority groups based on atomic number. So to rationalize the stereospecificity of this reaction, we need to consider the transition state for the reaction. In the transition state, the base is coming to take the proton attached to the beta carbon. There's a pi bond that's starting to form. So we have bond breaking occurring here. So as the base comes to take this proton, this carbon-hydrogen bond is starting to break. We have the formation of a carbon-carbon double bond starting to form. And we're also starting to break the carbon bond to the leading group, which in this case will be a bromide. And all of these atoms need to be in the same plane for the reaction to occur all in one step. And that's because the orbital that the carbon is using to form a bond to the hydrogen currently is an sp3 hybridized orbital, but it will be transitioning to a p orbital as we start to form this pi bond. Same thing here, this sp3 hybridized orbital that's being used to form a bond to the bromine will also be transitioning into an unhybridized p orbital. And both of those two unhybridized p orbitals need to be in the same plane to overlap to form a pi bond. So because of all of the stuff, all the bond breaking and forming that's happening all at once, the atoms need to be in the same plane. So we say that they need to be in what's called a coplanar arrangement. If you look at the structure of the alkyl halide, you'll see that there are two rotamers where those four atoms, the two carbons, the hydrogen, and the bromine, are in the same plane. In other words, there's two conformations where they are coplanar, all four atoms. Here we have a situation where we call this anti-coplanar because the bromine and the hydrogen are opposite one another, as opposed to when they're on the same side of the single bond, we call this syn-coplanar. So there's two different conformations where all four atoms are in the same plane. There's the anti-coplanar and the syn-coplanar conformation. We can look at the Newman projection drawn down the carbon-carbon bond, looking from the left to the right for each of these, and we'll see that the anti-coplanar transition state is in a staggered conformation, which we know is much more stable than an eclipsed conformation. And the syn-coplanar conformation, when drawn as a Newman projection, it will easily allow us to see that this is in an eclipsed conformation. So one of these two conformations is clearly more stable than the other. Of course, the anti-staggered conformation is going to be more stable than the syn-eclipsed conformation. So as a result, even though there's two coplanar conformations, this is the only conformation that allows for a reaction. This is a high energy conformation that is unlikely to exist very often. So the reaction will definitely proceed through the anti-coplanar transition state because it's lower energy than the eclipsed rotamer. So again, the base is coming to take the proton. This will become a p orbital that overlaps with the p orbital on the back carbon as the leaving group leaves. So all of that's occurring in the same single step, and we form a double bond, and we can represent that even in a Newman projection as sort of the molecule with the two carbons that are double bonded to one another and the groups coming off of that. So you can easily see the groups that are on the same side of the pi bond, which are the methyl and tert butyl on one side, and then phenyl and hydrogen on the other side. And because phenyl and tert butyl have priority, the E product is the only product that forms in this reaction. So some additional information. Evidence suggests that a strict 180-degree bond angle is not necessary for E2 mechanisms. Similar angles of around 175 to 179 are sufficient. So typically the term anti-periplanar is more commonly used instead of anti-coplanar to account for slight deviations from coplanarity. And although the E isomer is more stable because it is less sterically hindered, planar transition state can often lead to the less stable Z isomer. So in stereospecific E2 reactions, the E isomer is not always the correct product. Sometimes only the Z isomer, which is the less stable alkene, is produced exclusively because of the requirement for that anti-periplanar transition state. So the first activity that we're going to do today is going to look at the different anti-periplanar transition states when you have two hydrogens attached to the beta carbon. When there are two hydrogens attached to the beta carbon, it's any one of those two could potentially be removed to form the alkene product. So there'll be two possible anti-periplanar transition states, one with one of the hydrogens anti to the leaving group. And then as we rotate this hydrogen, it can also be anti-periplanar to the leaving group. And when that happens, we're going to see both E and Z products. So again, the stereospecific E2 reaction only occurs when both the alpha and the beta carbons are chiral centers. If there's two hydrogens here, clearly the beta carbon is not a chiral center, and therefore this will not be a stereospecific E2 reaction. It will likely be a stereoselective E2 reaction where we will see more of the more stable E alkene. That will likely be the major product. Again, because there's multiple different conformations leading to multiple potential stereoisomeric products. Okay, let's consider when we do an E2 reaction on a cyclic structure. So for example, some terminology first. So we've been talking about E2 elimination reactions. Those can also be called dehydrohalogenation reactions. So I don't want you to get confused by this really long name here. This just basically means we are removing the hydrogen and the halogen at the same time on a cyclohexane derivative. And so we will be doing an E2 reaction which removes both the hydrogen and the halogen. Those are just two different terms that mean the same thing. And the leaving group is going to be attached to the ring. We can actually look at the Newman projection down multiple carbon-carbon bonds simultaneously. So this one with the chlorine pointed up here is obtained from the viewer putting their eyeball over here and then looking down these two carbon-carbon bonds simultaneously. And what we'll see is that when the chlorine is in this axial position, there is a hydrogen anti-periplanar to it on one of the beta carbons, which would be here. There's also one here as well. But in this particular conformation, we're looking at the one here since we're looking down this carbon-carbon bond. Of course, this chair structure can do a ring flip. When it ring flips, the chlorine that is currently up and axial converts to up and equatorial. We can also look at the Newman projection where the chlorine is in an equatorial position. When it's in an equatorial position, the group that is opposite the leaving group is not a hydrogen. And as a result, elimination reactions cannot occur when the leaving group is equatorial, because those positions will always be blocked by carbon groups. Opposite them will never be a hydrogen. So even though the equilibrium favors the more stable chair conformation, which places the chlorine in an equatorial position, the E2 reaction can only actually occur when the chlorine is in an axial position because of the requirement for anti-periplanar transition state. So again, when the chlorine is equatorial, there aren't any hydrogens that are anti to it that can be removed on the beta carbons. But those do exist when the chlorine is in an axial position. So let's look at how that would play out with a different example. So can we figure out which of the two molecules below will not be able to undergo an E2 elimination reaction and why that is? And it says it might be helpful to draw their chair structures and build a model. Okay, so let's go ahead and practice drawing out their chair structures and see if we can figure out why one of these will not be able to undergo an E2 reaction and the other one will. Okay, so go ahead and draw any chair conformation of your choice. We are going to specifically want to draw a chair conformation where that chlorine is axial. So recall right now we know it's on a wedge, so it's up, right? But it needs to be in an up and axial position, not in an up and equatorial position. So easiest place to put it is probably here because this is a nice up and axial position. So in one case, we're going to have two hydrogens on one side and then a methyl on one side and a hydrogen on the other. So let's go ahead and put in those groups. And I might even label these just so we can clearly see the difference between the three of these. So we have the going clockwise, we're at this carbon. We've got HA that is pointing up, so it's going to be in an axial position. We have HB that is pointing down, right? So it'll be at this position, it will be down and axial. And then HC is also down. And the methyl here is up. Okay, so can we identify that there are hydrogens that are anti-periplanar to the leaving group? So both B and C, right, are anti-periplanar to the chlorine leaving group. Let's look at the other structure in a chair conformation. We could just draw the same chair conformation to be able to compare apples to apples. We'll place the chlorine in the same position. Here we can see that there'll be an up hydrogen. We can even label it if we want to. Right, we'll do A and call this D because it's a little different than those positions, but this is the same position, so I call it A again. So HA, we have the methyl, right? That's this methyl down here. And then there's a methyl down here and HD. Okay, so are there any hydrogens on the beta carbons that are anti-periplanar to the leaving group? No, right? So both of these are not hydrogen groups, right? So there's no hydrogens anti-periplanar. right? Which means no E2 reaction can occur in this substrate. Whereas, yes, we can do an E2 over here due to the requirement of a hydrogen and the carbons and the chlorine all being in the same plane during the reaction. So when you're looking at this, you don't always have to draw the chair structure. What you can remember is that in order for a hydrogen to be removed, it has to be opposite the leaving group. So if the leaving group is on a wedge, then the only hydrogens that can be removed are those on a beta carbon that are on a dash. So both of these are possible to remove. The hydrogens here are on a wedge and the chlorine is on a wedge. So these two hydrogens are not opposite the leaving group, and therefore they cannot be removed and to form an alkene in an elimination reaction. We want to look for the hydrogen on the beta carbon opposite the leaving group for the reaction to take place when the substrate is a cyclohexane derivative. So let's rationalize the product or products formed in these two reactions. So in this top substrate, we only get one product, whereas the bottom substrate, which has different stereochemistry, will have two products. So that's the first thing we want to rationalize. But as well, we want to talk about the information that is given here about the speed of the reaction. So this E2 reaction is slow, and this E2 reaction is fast. And let's think about how we can potentially differentiate when a reaction will occur quickly or slowly in an E2 reaction. And that's going to have to do with the fact of the two chair conformations and which one has the appropriate transition state in the more stable chair configuration. And let's go ahead and look at, talk about what exactly I'm talking about here. Go ahead and start to draw it out. Okay, so the first thing that we want to look at is the hydrogens, right? So there's the alpha carbon, there's the beta carbons. We can draw in all the hydrogens attached to the beta carbon because those are the ones that could potentially be removed in an E2 reaction. So we have a hydrogen that's down here, and we also have a hydrogen that's up and a hydrogen that's down at this other beta carbon. So recall that the only hydrogens that are opposite the leaving group can be removed. So the leaving group is on a dash here, so only the hydrogen on a wedge on this beta carbon can be removed. These two will not be able to get into an anti-periplanar transition state if we were to draw out the chair conformation, which we don't need to do because remember I told you you just want to look for groups that are opposite, and those will have the right chair conformation. So that's why there's only one product formed, right? So there's only, this is the only hydrogen that is opposite / anti-periplanar to the chlorine leaving group, which is why there's only one product. If we go ahead and analyze on the bottom here, we can again draw in the hydrogens attached to the beta carbons. And then we want to think about which ones are opposite the leaving group. So since the leaving group is on a wedge, hydrogens that are on the dash on the beta carbon are opposite. So now there's two, right? Both of these two. Two hydrogens are anti-periplanar, which is why there are two products formed. One is formed from the removal of this hydrogen, and the other is formed from the removal of this hydrogen at that carbon. Okay, and then we also want to think about the speed, right, of the reaction. So this one is slow, this one is fast. And in order for us to understand that, we want to actually draw out the two chair conformations or the substrate in each case. So draw one and then ring flip to get the other one. We can go ahead and draw one of the two chair conformations for this structure. You can do any one. It doesn't matter if the chlorine is axial or equatorial. Just any one is totally fine. I'm going to place the tert-butyl group up here. Okay, so let's place that there. And then this chlorine will be down. And that's one of the chair conformations, right? And then we can ring flip it. And when we ring flip it, this will become up and equatorial. And this chlorine will be down and equatorial as well, because right now it's down and axial. We will place it here. Okay, when we think about these two chair conformations, look at how we have both of these in an axial position versus both groups in an equatorial position, right? So this is much more stable, right? So we have the two groups, both equatorial, especially the big bulky tert-butyl group, which is really important to have in an equatorial position, right? It's very, very rarely going to ever go into this conformation. That's a problem for this reaction because this reaction requires that the hydrogen that is opposite it, which is this one, right? So these are the groups that are going to be removed. It requires that the chlorine is axial and the group that's opposite it will be removed to form the pi bond. And it's very rarely ever going to go into this conformation because it's very unstable with these groups being axial. Right? So the reaction must proceed in this conformation, which is very unstable or high energy. Right? So it's going to be very slow because first this would have to ring flip to this conformation in order to react. And remember that 99.99% of the molecules will be in this conformation at any given time, which is the wrong conformation for the reaction to occur. Let's look at this one. Go ahead and draw out again both of the chair conformations. So that tert-butyl, we'll go ahead and place that in the same position. The chlorine now is up. So we'll place it up here, right? And if we look at which one is more stable, right? Still having that big bulky tert-butyl group equatorial is going to be much more stable. The good news is that in this conformation, it is ready for E2 reaction because the chlorine is axial and it has access to hydrogens that are anti-periplanar to it. Right? So definitely this equilibrium favors this. It'll spend most of the time in this conformation, right? And the reaction proceeds through this conformation. So let's say most stable chair conformation. And then the E2 reaction proceeds with fluorine and hydrogen anti-periplanar. Okay. That was the end of the lecture for today. This lecture will help you to be able to complete not only today's activity, but you could also start on the activity for the next class as well, because that continues with the E2 reaction. And I completed the lecture on the E2 reaction today.